It's a special honor for me to be here. So first of all, because it's in Singapore, and this conference in Singapore has to take place so many times and was canceled because of COVID. All our lives were disrupted by this, and the fact that finally it's taking place is a great joy. But the second aspect I'm extremely sensitive to is to come to honor Zhang Weiping. So Zhang Weiping, in some sense, was my first Chinese student, coming at the time from nowhere. His coming was difficult. I had sent to him the preprint of my paper with Gilles Lebeau on quill and metrics, maybe wishing him to amuse himself with this preprint. Obviously, there was some joke in this dedication to him, but he took this very seriously. And when he arrived in Orsay, he had already absorbed a good deal of it. So I gave him to study a problem on eta invariance, which basically he solved immediately. I mean, at least he made the main steps immediately. So I was very impressed. And then we went out working on Raysinger torsion in the RAM context and Weinmeister the Chiga-Müller conjecture and so on. And it was always a pleasure to see him develop and mature by the day. So I wish him a great continuation in mathematics. And I want to say, as a teacher, that having him as a student was really a pleasure and a honor. So today I will speak about the hypoelliptic Laplacian and the trace formula. This is actually a question which is deeply connected to index theory in a context where there is no index at all. So what we shall see is that eventually a problem can be defined to be an index not because naturally it is an index, but because we make the effort to turn it into an index problem so that ultimately we can apply the methods of index theory. And one main tool will be the hypoelliptic Laplacian. So here is the organization of my talk. And so let me, first of all, explain possible connections between Euler characteristic and the heat equation. So first of all, the Euler characteristic. I give myself X to be a compact Riemannian manifold. Then, as you know, the Euler characteristic is an integer. It's a global invariant at the alternate sum of the dimensions of the cohomology groups of X. So let me give myself G to be diffeomorphism of X, which naturally acts on the cohomology of X. And so you can define its Lefschetz number, L of G, which is a supertrace of the action of G on the cohomology, the alternate sum of the traces in various degrees. So in particular, L of 1 is just the Euler characteristic. So let me remind you about the heat equation method. So basically you replace the cohomology by the de Rham complex, whose cohomology is the given cohomology groups of X. You give yourself a Riemannian metric on X, and you introduce the formula joint, dx star of dx. You form the corresponding Dirac operator, dx plus dx star, which is a self-adjoint elliptic first-order operator. You construct its square, which is a Hodge Laplacian. And there is a basic formula of McKinnon-Singer, which allows you to express L of G, the Lefschetz number, or if you like, the global invariant, in terms of the heat operator for the Laplacian, for the square of the Dirac operator. So you express it as an infinite dimensional quantity, supertrace of G times the heat operator. And this does not depend on S, positive. So for S equals infinity, it's obvious. In some sense, by Hodge theory, you see that the identity is obvious. The key fact is that it doesn't depend on S. And so by making S tend to 0, we get Lefschetz fixed point formula, or in the case of G equals 1, we get Schoen-Gauss-Bonnet theorem. So we express L of G, which is a global invariant in local terms, by interpolation between the two sides using the heat operator. So this is all well known. In particular, when S tends to 0, we can use local cancellations, as was explained by Petodi. So let's now move to an apparently different question. So let again X to be a compact Riemannian manifold, delta X to be the Laplace-Beltrami operator of X, acting on smooth functions, and then given T, positive fixed, I consider the heat operator, G, which is exponential of T times the Laplacian, scale Laplacian, which is a heat operator acting on smooth functions. So, as is well known, this is a trace class operator. So, I will ask 4 questions. Is the trace of the heat operator an Euler characteristic? More precisely, is it a Lefschetz number? So you see that this question is a bit strange, because if it was the case, that would mean that the smooth functions would be itself the cohomology of something. So the second related question is, in the same way as in index question, we replace the cohomology by the Dirac complex, can we do the same thing here? In other words, can we replace the smooth functions on X by what I call a resolution R? So a resolution R would be simply a complex whose cohomology would be the smooth functions on X. So now smooth functions on X become itself the cohomology group. And so that you could express eventually the trace of the heat kernel viewed as a Lefschetz number, again, as being the supertrace on some much bigger space, on some much bigger complex of G times the exponential of the square of some Dirac operator. But that Dirac operator should act on a bigger space now. So in other words, the smooth functions themselves become the cohomology of the game. And so we have to construct some bigger space, some bigger complex, with DRB a suitable Dirac operator. So by making B tend to infinity, exactly as when we had S interpolating between 0 and infinity, by making B tend to infinity, that would correspond to S tending to 0, do we obtain Selberg's trace formula? Selberg's trace formula is an extension of Poisson's formula for manifolds, locally symmetric spaces. So I will be more specific on this later on. So in other words, is Selberg's trace formula? Selberg's trace formula is a formula which evaluates explicitly the trace of certain heat kernels in terms of closed geodesics. So is Selberg's trace formula Lefschetz formula? So let me explain again the analogy. This line here, this was the interpolation I explained before between the Lefschetz number of a diffeomorphism, a global invariant, and a fixed point formula, or Poincaré-Gauss-Bonnet, which is a local formula. And so the construction to be done is exactly the analog of that one. On the left-hand side, we would have a sort of global invariant, which is a trace of the heat kernel. On the right-hand side, we would have Selberg's trace formula evaluated with closed geodesics. And in between, we'll have a mess. And it is this mess that we have to construct. So, first of all, let me remind you what is Selberg's trace formula for Riemann surfaces. That's the only case where explicit geometric formulas were known before, in some sense. So, Selberg's trace formula is as follows. You give yourself X to be a Riemann surface of constant scalar curvature minus 2, And you look at the closed geodesics, gamma, and then length, L gamma. So Selberg's trace formula expresses the trace of the heat kernel in terms of an infinite sum indexed by the closed geodesics. So you have essentially a first term, which is a complicated integral, and a second term indexed by the non-trivial geodesics. So I won't give the whole details, but let me simply mention that you see in the infinite sum the exponential minus the length square of this closed geodesics. And there is in the denominator 2 hyperbolic sine of L gamma of the length divided by 2. And also in the integral, you have again the A roof function. So we do see that this formula, even though not being an index formula, looks like an index to a certain extent. We see appearing our favorite function, in particular, the A roof function. You see that on the left-hand side, you have the trace of a heat kernel, which has been sort of transformed into a local expression. And it is exactly this sort of identity that we will eventually understand as being an index formula. So the right-hand side, this right-hand side is the various terms are called orbital integrals, in this case for the Lie group, reductive group G equal SL2R, but more of this later. So first of all, how can we view the space of smooth functions on X as being the cohomology of something? Naturally, as being the cohomology of something. So I give myself A to be a real vector bundle on X, whose total space is a script. And now, what I look at is at the relative de Rham complex. So in other words, on the fibers of E, you look at the de Rham complex fiber-wise. So omega ER are just the smooth forms along the fiber, and that's equipped with the fiber-wise de Rham operator. That's a relative de Rham complex. So it is a complex. And so if you apply Poincaré lemma, essentially it's a consequence of Poincaré lemma along the fiber. That's very easy. Which says that this cohomology is concentrated in degree 0. And that actually, the cohomology is just in degree 0, and that's exactly the smooth functions on X with values in R, because the cohomology is made of functions which are constant along the fiber. So, in effect, we have found many ways of expressing smooth functions on a manifold as the cohomology of some other complex. So actually, if you choose GE to be a fiber-wise metric, a metric on E, then there is a corresponding Hodge theory along the fiber. Actually, the proper Hodge theory is not the obvious one, doesn't consist in taking the Hodge Laplacian for the metric. It consists actually introducing some Gaussian weight, or if you like, introducing the Witten complex and the Witten Laplacian along the fiber. So that in effect, this complex computes the cohomology along the fiber, and the associated Witten Laplacian is a fiber-wise harmonic oscillator. So, of course, if I formulate the problem this way, I could choose any E. But of course, the rule of the game is to choose E properly. You're not going to get the formula by picking some random E. So we'll have to choose the vector E, and actually, in some sense, it's naturally to think that E will have to be connected with a tangent bundle to the manifold X. So let now me explain the effective construction of our object. In other words, of this Dirac operator dB. I will work in the case where X is first of all a symmetric space, and then we'll move to the case where X is replaced by a locally symmetric space, by a quotient, by a discrete group. So I give myself G to be a real reductive group. and K to be a maximal compact subgroup, X is equal to G mod K is a symmetric space. So if you prefer to be concrete, you could take G to be SL2R, K is S1, and X is just the upper half plane. Then I consider the Lie algebra G's fracture of the reductive group and the corresponding Cartan splitting. In the case of SL2R, it just corresponds you look at trace-free matrices and you split them into the symmetric part and the antisymmetric part that corresponds to P plus K. So this splitting of the Lie algebra, since it's a K representation, it descends by quotienting by K to the bundle of Lie algebras. There is a piece which is Tx, the ordinary tangent bundle to the symmetric space that corresponds to the P part, but there is also an extra part which is N that corresponds to the K part. And actually, ultimately, the analysis will be done on the total space of Tx plus N over the symmetric space X. So I will now explain the construction. So the advantage of working on a symmetric space is that we will, in some sense, dissociate, first of all, the group G and the Lie algebra G fracture. We'll dissociate them. We will proceed as if they were independent pieces. And then eventually, by the quotienting, we will connect them. So the analysis will be done on G cross Lie algebra quotient by K, which is a total space X hat of Tx plus N over X. We will do two separate constructions on the group G and on the Lie algebra G fracture.
What is N?
N corresponds to the K part of the Lie algebra, right? You have P plus K. So if we're in positive curvature, you would have the sphere as symmetric space. You would have the tangent bundle, Tx. And the other part, N, would be the normal bundle. Okay, that exactly in the negative curvature, you can do the same thing. So you see that for the moment, there is no Dirac operator whatsoever. I'm computing the trace of the heat kernel, that what I want to do, on functions. There is no Dirac operator. And we're going to force the formalism of Dirac operators in this context. So let me remind you what is the Dirac operator of constant. So first of all, on the Lie group G, there is the analog of a Laplacian. If the group was compact, it would be an ordinary Riemannian Laplacian. Since the group is reductive, the natural metric on the group splits into two pieces. It's not a metric. It is positive in the P part and negative in the K part. And there is a corresponding fake Laplacian, which is written as minus sum of E star I EI, that the Casimir operator. It's not elliptic. It is more or less hyperbolic. It is a difference of two elliptic operators. So that's a bad operator. Its symbol is positive on the P part and negative on the K part. That's a Casimir operator. Let me introduce the Clifford algebra C hat of the Lie algebra. So the Lie algebra is equipped with a symmetric form. Again, the symmetric form is B. If you like, it's a killing form, positive on P, negative on K. And I introduce the Clifford algebra of G minus B. As we know, the Clifford algebra acts on the exterior algebra of G star. So I finally introduce U of G, which is the enveloping algebra, that's the left invariant differential operators on G. So the constant Dirac operator is not the Dirac operator in the Riemannian sense, not even in the pseudo-Riemannian sense. Because G is a pseudo-Riemannian manifold, it carries naturally a Dirac operator. Constant Dirac operator is a mild modification of this. So the constant operator, I didn't give the explicit formula here. It's essentially, again, there is a Clifford algebra, sum of C of EI, C out of EI, differentiation direction of EI, and then there is an extra term of length 3. That's the constant operator. So this operator is a matrix operator. So let me give a formula of constant. So what constant proves is the following, that in the same way as Dirac, when introducing the Dirac operator on R4, found a differential operator whose square is the Laplacian, what constant found is that the square of this Dirac operator is a scalar operator. It is essentially a scalar modification of minus the Casimir. So it's an almost square root up to a constant. So what you see is that on the right-hand side there is no Clifford matrix at all. It is just purely, in some sense, acting on smooth functions. On the left-hand side, you have a matrix operator whose square is the scalar operator. So it's, in some sense, a strange situation that we find the square root of an operator, but this square root acts on a different space than the original space on which the Laplacian or the Casimir acts. We found a square root, but in the wrong space. So apparently we cannot do anything with it. And that's precisely going to make this intuition lie. We're going to use the fact that the Casimir is actually up to a constant, the square of this Dirac operator. So actually, this Dirac operator of constant, it acts on smooth sections on the group of the exterior algebra, if you like, on the Dirac complex of the group, while the Casimir acts on smooth functions on R. And so we're going, in some sense, when solving the problem, in some sense, forcing the introduction of the exterior algebra of G star. So let me move now to the case of the Lie algebra. I told you there are two constructions, one on the group, the other on the Lie algebra. The one on the group involves the constant operator. The one on the Lie algebra, that's in some sense for us an easy one. So, first of all, the Lie algebra is not an Euclidean vector space because the form is positive on one side, negative. We're going to do a Wick rotation. We're going to replace k by ik. So that this Lie algebra modified Gi now becomes an Euclidean vector space. And this Euclidean vector space carries also a harmonic oscillator. So here is the harmonic oscillator, written in the classical form. But actually, as we know, on this Euclidean vector space, there is the Witten complex, which I wrote in this way, which consists in twisting the classical Dirac operator on the modified Lie algebra, taking its adjoint. All of this acts on smooth sections over the Lie algebra of the exterior algebra. Okay, so this operator is a Dirac-like operator on the Lie algebra, or a modified version. And actually the corresponding Witten Laplacian is the sum of the harmonic oscillator and the number operator on the exterior algebra. So let's think a bit. We have done two constructions. One on the group. We found a Dirac operator acting on smooth functions on the group with values in the exterior algebra. The other one, on the Lie algebra, we also found a Dirac operator, which in some sense is more natural. That's the obvious one. And now we're going to couple the two constructions. So let me introduce the operator dB, d factor b. So this will be a combination of the Dirac operator on the group and of the Dirac operator on the Lie algebra. And what we couple these two operators will be that they act on the same bundle, which is the exterior algebra G star. So this operator dB will act on smooth functions on G cross the Lie algebra with coefficients, if you like, in the complexified exterior algebra. This is not so important, the complexification here. So let me give the formula for dB. Please ignore for the moment the red part. The operator dB will be simply a linear combination of the constant operator, which acts on the group, and of the Dirac operator, the Witten one, acting on the Lie algebra. You do the obvious linear combination with a factor 1 over b on one of them. So that when b tends to infinity, actually the constant operator dominates, and when b tends to 0, it's the fiber-wise Dirac operator which dominates. And there is a third term. This third term is nonlinear. It's a quadratic term. I will not explain for the moment its origin. Since it's in red, it is the most important term, I would say, because without this term, the theory would not make sense. But however, for the moment, please ignore it. So, our fake Dirac operator is now K-invariant. It's obviously K-invariant because all the constructions we did are invariant under the action of K. So the operator dB descends to an operator on the quotient. So now we come to the hypoelliptic Laplacian. So what I'll do is that, in some sense, I should take the square of the Dirac operator dB square. But what I'll do, I will explain later on. This looks a little bit tricky. Why do I construct this difference between dB square and the square of the constant operator? So remember, essentially dB is a sum of constant operator plus the Dirac-Witten operator. If we square it, we have a squared plus b squared plus ab bn. If we subtract a square, we just are left with an anti-commutator plus the square of the Dirac operator on the fiber. So this is our operator LB. And then we quotient the construction by K. This we are allowed to do because simply all our constructions, our group are K equivariant. So again, let me remind you that G, the Lie algebra, descends to a vector bundle on X, which is Tx plus n. This Tx plus n will play the role of the vector bundle E, I mentioned in my talk before. So I introduce this operator LBX after descending, which again is written in this form, and this acts on what does it act? It acts essentially on smooth forms on X script hat with values in the exterior algebra of T star X the base and N star. So first of all, let me give the form of LBX. So LBX actually is not an elliptic operator on this bigger space. It is actually hypoelliptic. So here are the pieces in red. The first piece in red is the harmonic oscillator on Tx plus n. Remember, this one we understand. On this fiber Tx plus n, modulo the Wick rotation, we have a Euclidean vector space and there is a harmonic oscillator. This requires a weight 1 over b squared. There is a second piece in red, which is essentially, okay, I wrote it as nabla in the direction ytx. So y in the direction of the fiber splits into ytx and yn. I take the component ytx and I view it as a differential operator in the base, on the base. So in other words, this nabla ytx is a sort of version of the geodesic floor. So I have a bunch of matrix terms, and what I also have, the first term here, is a quartic term, which is of degree 4 in the fiber variable y. So we have departed from the harmonic oscillator. We have an operator now which is no longer harmonic oscillator. It contains a quartic term. So why is this operator a good operator? It's because it's, in some sense, even though not being elliptic, it is hypoelliptic in the sense of a Monta, and it also has a heat kernel. So this operator, by ignoring the quartic part, looks like a Fokker-Planck operator in statistical physics. And there is a basic fact that I will not explain, which says the following, that even though the operator LBX as B tend to 0 seems to blow up, as B tend to 0, all the pieces in some sense blow up, but actually this is a wrong perception. Actually, I'm saying that essentially LBX as B tend to 0 deforms the original Casimir operator on the base. So in what sense is this true? One could say that if I, instead of looking at the operator, I would look at its resolvent, or I would look at its heat kernel, it would be correct to say that there is a corresponding convergence as B tend to 0 of the heat kernels. This is correct. So maybe a final word on the introduction of this quadratic term in the construction of dBx. If the quadratic term was not there, the square we would obtain without this one would be a bad operator. Actually, would be an operator which would not have a heat kernel. There is actually the quotienting by K introduces some non-linear coupling between the base and the fiber, which makes that potentially the operator we would obtain would be bad. So to correct this potential analytic badness, we had to also to correct the Dirac operator. So let me now move to the case of locally symmetric spaces. So I give myself gamma to be a co-compact torsion-free subgroup of G. So if you like, in the case of SL2R, you give yourself a discrete subgroup of SL2R, which is compact and torsion-free. So this in particular means that gamma acts on the symmetric space X without fixed points. And so the quotient on the left of the symmetric space by gamma is compact locally symmetric, which means that it is a compact manifold. So let me state a fundamental identity. So this identity tells us that the trace essentially of the that the heat kernel, okay, CJZ, this CG over Z is essentially the Laplacian on the smooth functions on Z. Okay, that's actually exactly the Laplacian. And there is this correction, this translation by a constant that I will not explain. So the trace of the original heat kernel on smooth functions is given by the supertrace, alternate sum of traces of the hypoelliptic heat kernel. And this for any B. This for any B. So this identity should be thought of as being the analog of the Machin-Singer we were looking for. In the Machin-Singer formula, we had the trace, the left-hand number, the trace or supertrace of the action of G on the cohomology is given by the supertrace on a bigger space, on the de Rham complex. Here, we have exactly a formula of the same structure, that now the trace of a heat kernel is given by the supertrace of exponential minus t LZB. So, let me try to explain actually why is the right-hand side a Machin-Singer formula. So I had told you that this LB, there was something fishy that I had done when introducing LB. I wrote it as a square minus a square. So that's exactly what I do. I rewrite LBZ as being the square of the Dirac operator dBz minus the Casimir. And so if I write it this way, this line here, this last line is just a reproduction of the right-hand side. You see that this has to be compared with the supertrace in Lefset's case of G times the exponential of the square of the Dirac operator. It has exactly the structure of a Machin-Singer formula now. Okay, is that the logic which underlines the fact that we had to construct LB in this way? Splitting the identity. Now, each side splits as a sum indexed by conjugacy classes in gamma. Okay, so this looks complicated, but if you have the classical heat kernel on Z, on the quotient, you can express the heat kernel itself as a sum over the discrete group on the universal cover, as a sum indexed by gamma. If you group all the terms together, ultimately these sums splits as an infinite sum indexed by conjugacy classes in gamma. This is true for the left-hand side. It's also true for the right-hand side. And so what I'm saying is that actually the identity I gave before splits. Each side is a sum, and actually there is an identity term by term. That's an identity of so-called orbital integrals. So let me briefly explain what these orbital integrals are. So now we are going to work exclusively on the symmetric space in the non-compact setting. So let me take gamma in the Lie group G to be a semisimple element. Well, if you are in one of the classical groups, that means simply that gamma is diagonalizable, properly diagonalizable. I will give a more geometric interpretation of this diagonalizability later on. So I call bracket gamma its conjugacy class. So then, you can introduce the associated orbital integral of the heat kernel. So for the moment, if you like, make E to be the trivial vector bundle so that PTX is a scalar heat kernel. And so this orbital integral, what is it? Essentially, it's the integral of the scalar heat kernel on X evaluated on the orbit of gamma by the Lie group. So this looks like a complicated formula. I will give a very much more geometric version. This integral actually is evaluated on the left quotient of the Lie group by the centralizer of gamma. So this looks like an abstract quantity, and I will give now a concrete form of this orbital integral, concrete geometric form, geometric description of the orbital integral. So, okay, this is a very short thing. So, given a semisimple element, you can introduce on the symmetric space the so-called displacement function that the function d gamma of x, which is d of x and gamma x. Gamma acts as an isometry of the symmetric space. And because of negative curvature, this is a convex function. Convex function means that it is convex along geodesics. The fact that gamma is semisimple exactly means that the inf of this displacement function is reached, that you effectively reach is of gamma. In other words, this takes its infimum on this manifold x of gamma. So x of gamma is a totally geodesic submanifold of x. And actually, it turns out to be the symmetric space. It's the symmetric space. It's itself a symmetric space associated with the centralizer Z of gamma. Okay, so in other words, in X, you have this submanifold X of gamma, where a certain convex function is minimized. In the case of the hyperbolic plane, X of gamma would simply be a geodesic line. And so actually, the orbital integral is obtained as follows. You take a normal to this X of gamma, you take a normal, and Y, the generic point at the normal, you take its image by gamma. Gamma maps the normal at x0 into the normal at gamma x0. And you take the heat kernel evaluated between Y and gamma Y. Because of negative curvature, these 2 points, Y and gamma Y, their distance grows at least linearly in the direction Y. They cannot be parallel. It grows. And the orbital integral is just the integral of the heat kernel along these normals. And because the distance grows linearly, we essentially have at infinity a Gaussian-like integral. This is the orbital integral. The hypoelliptic Laplacian method, making B tend to infinity, means that we're going to localize the integral near x of gamma. There will be this process of localization of the integral on x of gamma. So let me state the second fundamental identity. That's a refinement, a harder refinement of the identity I gave before, is the invariance of the orbital integrals under hypoelliptic deformation. So both sides do have orbital integrals of this kind. One, in some sense, is a classical one. The other is non-classical because we have made this, it's on a bigger space, but nevertheless, the orbital integral is invariant under the hypoelliptic deformation. And now we're going to make B tend to infinity. Making B tend to infinity will force localization on x of gamma. That's the analog in Mackin's singular formula of making S tend to 0. So when B tends to infinity, the operator LB, essentially after rescaling, you see the dominating factor is actually, there is this commutator, which is very big, but there is a constant term, which is essentially the geodesic floor. So that means the heat tends to propagate along geodesics. So the orbital integral, in the end, localizes near this x of gamma, the minimizing set of the displacement function. And actually, it's in some sense the manifold of geodesics in x associated with gamma. So let me try to explain what the formula, explicit geometric formula for orbital integral looks like. actually the formula will be express the orbital integral as an integral over a Lie subalgebra. So let me again introduce Z of gamma to be the centralizer of gamma. And its Lie algebra again has a Cartan splitting. It splits into its P of gamma and K of gamma part. Semisimple orbital integrals. So this is a promised formula for these orbital integrals that generalize to arbitrary reductive groups, the formula of Selberg. So there is an explicit function J gamma of Y0K. So Y0K, again, you had this Cartan splitting of the Lie algebra PG equal P plus K. When you look at the centralizer also splits Z of gamma, the Lie algebra, equal P of gamma plus K of gamma. So that's an integral over K of gamma of a function J gamma. And J gamma will be an analog of the Héroux function. That's an analog of a Riemann-Roch formula, actually. The formula I will state. So the formula says something as follows. The orbital integral associated with the heat kernel is equal to, forget for the moment about the E piece, forget completely, it's equal to the integral of this function J of gamma with respect to the heat kernel on the K of gamma piece. When looking, instead of looking at smooth functions, you look at sections of a vector bundle, you have an extra term, which is this trace, which is written here. This formula should be viewed as an analog of the Atiyah-Singer or Riemann-Roch-Grothendieck formula. In this last case, we had the pairing between the Héroux class and the Chern character. We have exactly the same sort of structure here. J gamma plays the role of the Héroux class. This is now a function on the K of gamma part of the centralizer, and this is integrated with respect to the Gaussian kernel. There is as a factor exponential minus a squared over 2t. This corresponds to the minimizing length, to the minimum of the displacement function. I had told you there was a displacement function which has a minimum. This a squared is just its minimum. So let me show to you how does a function J gamma look like. Well, the function J gamma looks a bit intimidating. That's again a function on the K part of the Lie algebra of Z of gamma. So actually, the Lie algebra G splits exactly when you have fixed point formulas. You lose a splitting of the tangent bundle at the fixed points under the action of the isometry you look at. These are Lefschetz formulas for Dirac operators. You have exactly a similar things here in which you look at the action of gamma itself on the Lie algebra. Okay. The key difference is that in the case of the index theorem, you just have the Héroux of tangent bundle paired with Chern character. Here you have Héroux of the Tx quotient by the Héroux of n. It's as if this splitting of the total bundle Tx plus n induced at the level, at the localized level, exactly now at an index formula, but in which Tx and n play opposite rules to each other. Let me, of course, point out that when you specialize this formula to the case of SL2R, you recover Selberg's original formula, which contained the first term, which was an integral over R, which is exactly of the kind I said before, plus a discrete sum This discrete sum here takes because the centralizer is just, or the Lie algebra is trivial. So there is no k gamma part at all. So let me give an application of this. So let me look at Pt of x to be the smooth kernel, heat kernel on R. So given A in R, Pt of A is in some sense a special case of an orbital integral for the reductive group R. That's a special case. If you use the invariance under deformation of the orbital integral, you express Pt of A as being the supertrace orbital integral of the hypoelliptic heat kernel, which is a heat kernel acting on R2 now. There is no k part, just p part. And if you make b tend to infinity, what you get is a formula for Pt of A. That's a special case of a formula I gave before, which is given by the classical formula of the heat kernel. So the left-hand side, Pt of A, is now an index, and the index formula takes the form of the right-hand side. And it has been obtained by interpolation. So of course, the point of this is not to obtain this formula. The point of this is simply to show that this formula now, in our language, is an index formula. The left-hand side is analytic, the right-hand side is geometric, and we found the formula by interpolation between the two sides. Of course, the content here is trivial, but it's just to give an example. So let me explain finally an extension of this formula to the center of the enveloping algebra. So the formula I stated gives a special role to the Casimir operator. The Casimir operator, again, is a differential operator on the Lie group, and it lies in the center of the enveloping algebra. It commutes with all the others differential operators, left invariant differential operators. But actually, the enveloping algebra has a bigger center. So let me call Z of J fracture to be the center of the enveloping algebra. So the center of the enveloping algebra, this is a non-commutative Lie algebra, and it has a center, which is a commutative algebra. So let me call I of G fracture to be the invariant polynomials on G star. So on G fracture and on dual, you have an adjoint action of the Lie group. So you can introduce the invariant polynomials on G star. So what is the Duflo isomorphism? The Duflo isomorphism, it's a non-trivial isomorphism between the polynomial algebra which I gave before, I of G, and the center of the Lie algebra Z of G. So it's a filtered canonical isomorphism of algebras, tau D. So that, in particular, if you look at the Casimir operator lies in the center of the Lie algebra of U of G. So its image via the Duflo isomorphism, actually you could view this as almost being the principal symbol. So actually what you find is that the image is given by minus B star. B star, okay, you have the Lie algebra is equipped with a symmetric form B. It induces by duality a symmetric form B star. So B star actually is a polynomial of degree 2 on G star. So in other words, the Casimir its image via the Duflo isomorphism, it's not simply minus B star, it is minus B star translated by a constant. Okay, so if you like, this Duflo isomorphism is a sort of principal symbol map, but which is in general highly non-trivial. Yes?
Does the Duflo isomorphism have analytic kind of expression?
Sorry?
Does it have a closed-end kind of
Oh yes, there is an algorithm, in other words, to compute, to find the correspondence. This algorithm is the one which reduces this B star, this correcting term. Yes, there is an explicit, it's an algorithm, but it's a complicated algorithm. I will not explain that. So in other words, these two algebras are isomorphic as algebras. Okay, so I give myself L now to be an element of the center of the enveloping algebra, Z of G fracture, and I look at its image in the I of G. So this is a polynomial, invariant polynomial on G star. So by restriction, this invariant polynomial on G star gives an invariant polynomial on Z of gamma star. You have Z of gamma, which is embedded into the Lie algebra G. By restriction from a polynomial, you get an element, an invariant polynomial on Z of gamma. And so there is a corresponding from this polynomial, there is an associated differential operator on Z gamma with constant coefficients. In other words, you take an element of the center, you get a polynomial, you restrict it, and from the restriction, you get a differential operator with constant coefficients. Okay. So let me give the formula for general now sort of orbital integrals. This is the theorem that I proved with Shu SHEN in 2019. It will in some sense give a similar evaluation, a similar geometric evaluation of the orbital integrals, but for sort of general heat kernel or general operators involving the center of the universal enveloping algebra. So on the left-hand side, you have, this is best formulated introducing the corresponding wave kernel, but if you like, you could simply take mu to be the Gaussian. So you would get trace orbital of integral for gamma associated with the heat kernel times L. So in other words, the true difference with respect to what I did before is that I do not have only the heat kernel for Casimir, I also have a correcting term which is this L as a differential operator. And now I give a formula, a sort of local formula for the orbital integral of such objects. So again, I will not comment in detail, but this can be evaluated exactly as when I had before the integral with a heat kernel of the K of gamma part. I do have a similar integral, but in which the extra factor L is replaced by its proper image as a differential operator on Z of gamma. Okay, so this should be viewed again as an index formula. The left-hand side is global, the right-hand side is local. Left-hand side involves the Lie group, the right-hand side involves purely the Lie algebra. So the method of proof consists in effectively saying as follows: when L is equal to 1, this is just the previous formula that I showed in the case of the heat kernel, and actually you have different stages where you have to analyze gamma in different types. I mean, this I will not give too many details, but basically, you have to use methods given by Harish Chandra to be able to, first of all, evaluate the integral when gamma is a regular element. I mean, gamma being regular means that its centralizer is a so-called Cartan subalgebra. I will not go into that, but I mean, there are various degrees of degeneracy. It's a sort of complicated proof in various stages where you use the explicit evaluation in the case of the Casimir plus methods of Harish Chandra. Okay, so here are the two relevant references for my talk. And finally, for Jean vaping, happy birthday. Thank you.